Okay, good afternoon, everybody. So we share the presentation with Boutros and me. So I'm not very proud about the title because it's not very clear, but I hope after the presentation it will be more clear. So we come both from the Nantes University, so in the west coast of France. We have a joint laboratory between University of Nantes, École Centrale de Nantes, and CNRS. And so in this laboratory there are six groups. And one of the group where I'm from is working on this subject. So we will deal today with, we will speak about the gamma models and risk-based inspection, so more about gamma models. So we work on time and space-dependent degradation modeling and computing. So goal-oriented sensors, so what we call HLB fiber optic sensors that allows to measure 3D stress in concrete. 2D patch fiber optical sensors and sensors to assess spatial variability in concrete. So, and we work on operational monitoring too. So that's 2D cases. So mainly about with caves and wharves. One wind turbine, and next year and the next after we will probably monitor one concrete floating structure and one jacket. Okay, so we share this presentation so with two steps. The first one is will be presented by Boutros, and the second by me. They are both related to the real quantification assessment. I mean what we call the error measurements, but that's incomplete and imperfect measurements that are due to technical, human, numerical limitation, and of course epistemic uncertainties, and that contribute to an estimation that you have already seen. So when you look to the benefit here. So you have here so that's come from this paper. You have here the uncertain information from SHM, and this uncertain information from SHM can be affected by incomplete, so that's X minus here, and imperfect information, so that's the uncertainty on the monitoring itself. So that leads to reduced information, so we don't have all the information that we could have. So Boutros will speak about that. And this one could lead to bad decision if we cannot filter it. So the first presentation showed us how to identify that, but if we cannot, of course, it could lead to bad decisions, and I will focus on it. So I will give the microphone to Boutros.
So hi, I'm Boutros, and I will present the second part. So it's about quantifying the benefit of using multivariate and multiphasic degradation using stochastic processes. Okay, so currently I'm engaged in a short-term scientific mission between University and Nantes, and I'm hosted in Trinity College Dublin with Professor Alan O'Connor. We're working on how to take into account erroneous databases or erroneous incoming data into the prediction and the amelioration of prediction of degradation. And we also consider environmental affected parameters, such as climate change, for example. So first, I put the context of this work. So pathologies which are treated here are mostly, for example, corrosion. They are slow processes in time, and they are multiphasic. So we have different phases, but generally, like as we saw in some of the application of the SHM, we focus on one measurement, such as crack width. But in reality, we have different indicators, and these indicators, all of them, they are related to the same failure. So for example, failure of structure or, I don't know, initiation of corrosion. So we have different indicators that reflects this. And these indicators have different tendencies. So we need also to, if we were taking into account all these indicators, we need also to figure out the correlation and the tendencies of these indicators. So if we combine, if we use, for example, two indicators to model a degradation, for example, we can have many benefits, such as we can model unobservable degradations, where we have a sort of potential of degradation inside. For example, corrosion. We have the corrosion which motivates the cracking, but it's rarely taken into account. We can model imperfect maintenance action, especially where we can model actions that do not bring the structure as good as new, and we still have some sort of degradation inside the structure. And we can further individualize structure, where, for example, we have two structures, two crack widths, but what's happening inside, we have one that is much corroded than the other, or its potential of corrosion is much higher. So in the prediction of the degradation, the one with higher corrosion, it's most likely to as a consequence, have faster growth of crack. So this is rarely taken into account as well. So in this, from this perspective, we try to quantify the benefits in terms of life cycle management and SHM of considering multiple indicators of the structures. Where we have, if we take all discretize pathology into its phases, its major phases, and we will look into indicators in each phases, we will have, we can catalog different inspection techniques and specific maintenance actions to each phase, which will help us optimize the monitoring, which is where we can find, for example, type of monitoring or quality that is enough for us to quantify or to optimize the monitoring and the life cycle. So first, I'll introduce the state-based meta-models, which allow us to take into account different indicators and correlate them using a formulation of stochastic processes. So meta-models are based on three big elements. In the first element, we have degradation analysis, where we look into the pathology and what constructs it and how many phases. So the aim here is to give physical meaning to the processes we're trying to model. The second phase is we give the appropriate stochastic processes and the correlation functions between the indicators to respect the tendencies. The third one is we analyze the maintenance. How can we inspect them? Are the indicator, we can inspect them via SHM or not, and do they impact decisions and as such. So to define the approach, the aim is to arrive to a small number of parameters. For example, we modeled chloride-induced corrosion, where we want, so for example, the cracking phase in the current models is in physical models is about 50 parameters, whereas in formulation of stochastic processes, we can go down to 9, which is helpful in calibrating models. Second is meta-models are based on probabilistic pertinence and physical expertise. Third is indicators of degradation is based on indicators of degradation and durability directly accessible through SHM. So for example, here I will show a fast example. Chloride-induced corrosion. We have the three phases, which is diffusion of chlorides, corrosion initiation, and the cracking deterioration phase. If we have these three phases. So what if we were to model each phase using two physical indicators that we will call rho and theta, and where rho will be condition indicator. For example, for the deterioration phase, rho will be the crack width, and the theta for that phase will be the corrosion current density. The choice will be based on their accessibility via SHM and how much it represents the process, so how much it impacts decision. So for example, for this pathology, we have these physical indicators which we can inspect, and they give the most important knowledge of or most valuable knowledge for each of the three phases, so we can adequately predict or calibrate the models. So in order so the second step was to give the stochastic processes to respect the patterns of degradation or the tendencies. So we can find from in the literature or from data sets how this type of indicator will evaluate in time, and we can make the model to respect this. So we have for the first phase these shapes, tendencies, these tendencies, and then to model the transition between phases, we put on the rho, which is a condition indicator, a limit, a threshold. For example, there we have the chlorides, then we have the the second one is for tensile, ultimate tensile strength. This is the threshold. And then we go for the third phase, where we have fixed by Eurocode for the crack, because we will focus on this one for failure. We can notice similar shapes between tendencies. So we have L shapes and S shapes. This will help us a lot in calibrating or mathematically formulating the model. So one interesting result from using multivariate to model a degradation, we can result in bivariate, for example, calculate bivariate quantities such as probability of failure in the next interval based on these two observables. So if we were, for example, to go inspect the structure for these two indicators, we can have function of the state represented by these two indicators, a probability of failure. This will help us to change the way we look at decision making, which mostly was based on a one indicator or for example, crack width, and this is above it, it's not safe. Below it, we're safe. So this will help us. For example, we have points that are joined or states that are joined by the same probability of failure. So we have a contour, and below it we have an acceptance risk area. Above it we have a critical risk area. While we compare it to the traditional one, where we have one limit, we can see we have two regions of inadequacy, where we have, for example, here, for like the Eurocode, if we are below a certain level of cracking, we might be in a high corrosion current density, which signifies that we are not, that degradation will grow faster, and this can be considered as not an accepted risk area. Over there, we are above the crack, but we are below the contour, so also same analysis can be done. So one of the benefits of using this approach is we can benefit from the stochastic nature of the model. So for example, if we have 3 sensors that are in time that are recording coming information, this information might suffer from erroneous from errors, such as if we have all point, we can estimate the model using maximum likelihood estimation. However, we might suffer from erroneous data, such as censorship. We are below the detection of the machine, or truncated the machine, or the sensor stopped working, or we have missing points for faulty cable or something. So this one of the benefits of using stochastics, that we can benefit from algorithms such as stochastic estimation maximization, which allow us to estimate the missed or the erroneous data based on current one we have, and this will allow us to better fit the model to predict the degradation. So it will increase our confidence in the degradation. Another approach will be to benefit from heterogeneous databases. This is where, for example, we have a family of structures, and the structures we have recordings, and for some reason the sensors and the structures stop. But at the same time, we have a next structure which is similar or in environment and in function. And we installed a new set of sensors, so we might benefit from the new sets of sensors to ameliorate our confidence in the prediction of redegradation. So this will end my part of the presentation. I'll give back the micro to. No, not this one.
So the second and last part will be shorter. I will only remind few things about the probabilistic modeling of SHM results when you have error. So we start from the SHM system and or non-destructive testing. We have a consequence analysis and a structural network with limit states, so the mechanical model, and it allows to compute or to analyze the risk. And if you if you have harsh environments, or if you have a lot of errors in your systems, bad detection exists. So that could be the detection of a non-existing defect or the non-detection of an existing defect, and that will lead to bad decisions. So mainly to overcost, to non-necessary repair or failure. So there are some concepts, so that was published already by John, Michael, and other people that allows to quantify that, and I only want to remind that today. And that's the RBI deals with this part of uncertainty in the inspection process. So we have to model this uncertainty, and we have to take into account the expert judgment, if there is, and model its choice. So there is the real world with natural hazard, so that's behind the picture here, and the accessible world, so that's what we can measure. And to go from here to here, we select this approach, so probabilistic modeling of inspection based on this detection theory. The Bayesian modeling of inspection result, and we will see why after, and the introduction of expert judgment. So that is here, that's the gamma function, that's the probability to have the defect really. So that could be done by a model or by an expert, and that is needed to compute some probabilities after. So I will explain that after. So the two main concepts we will first focus on are the probability of false alarm and the probability of detection. So I start from a very simple example, only to illustrate that. The case of corrosion, where you have no corrosion or you have corrosion, that's the real inspection. You can see that it's made in very harsh conditions. The sensor is not easy to put in on the structure. And of course, if you detect something that is existing, you have a probability of detection. And if not, you have the probability of false alarm. So you detect a defect that is not existing. And so how to compute that? How to assess this probability of detection and probability of false alarm? There are mainly two ways. The first one is a statistical approach. So you know the real size of the defect, and you measure with your system this defect. So that's very costly because that's an intercalibrated approach. So you need put that in the field to account for the uncertainty due to the field and to the reality. And it was performed in the ICON project. That was a GIP project by 20 years ago, 30 years ago, and I think that there is no more project for making that until now, so that's very, very costly. And of course, you can define the non-destructive threshold level by doing that. So the second one is the signal analysis approach. So you know what is the noise density probability and the signal plus noise density probability. So you have a detection threshold somewhere here. And so the probability of detection is the probability that the signal plus noise density is more than this detection threshold. And the probability of false alarm is represented by bricks here. So that's the probability that the noise only is more than your detection. And for using, if you want to use that, you need assumption on the real value of the real defect, because you have to know what is the error. So you need a reference somewhere. Error modeling, so what is the distribution and the expert judgment, and assumption on the detection threshold level if you want to quantify this probability of detection. So I will illustrate that now. So we start from in red from distribution of errors that will not be changed depending of the defect size, and we will increase the defect size, and we will compute the probability of detection depending of the defect size. So by increasing the defect size with a constant standard deviation here, of course you detect more and more easier the defect, and the probability of detection is almost 1 when you are in this situation. If you want to consider the false alarm now, you have to consider one of these situations, for instance this one, so the third one, and you move the detection threshold. So in that case, you will change the probability of false alarm here and the probability of detection. So by moving in this direction, you are decreasing the probability of false alarm, but decreasing the probability of detection too. So there is an optimum. That is the point, of course, that is closest to this point, that is the base performance point here, with probability of detection equal to 1 and probability of false alarm equal to 0. And that can be parameterized, and you can analyze the effect on the risk-based inspection of this point. Okay? And the whole curve here is the receiver operating characteristic curve, so that's called ROC. Okay. So what we have is in lab is NDT optimal or SHM NDT optimal performance. So that's not very useful. So you need on-spot checking to assess how the NDT is easy to use and the divers, for instance, if you have the corrosion, and the topside operator affects the probability of detection and probability of false alarm. But what we need is not the probability of false alarm or probability of detection, but that other probabilities that I will define now. And these probabilities will be in the decision term, which allows in the decision term to account for a bad decision and good decision and the consequence of that. So what are these probabilities? So I illustrate only two of them, P1 and P2. What is needed by the owner is not the probability to detect something that is existing, but to decide that something is existing, knowing that has been detected. So that's the inverse in terms of conditional probability in the Bayes theorem. So of course you can compute the probability that there is no defect, knowing that you decided that you made no detection, for instance, this probability, and the probability that there is no defect, knowing that you made a detection. So that depends on the, that is a function of the probability of detection, the probability of false alarm, and the probability of crack or corrosion presence. So that's why these gamma were introduced before. Okay, so conclusion and interaction with work package. So we try to explain how to define the optimal detection threshold once the system is defined, to quantify the consequence of bad decision, and to include multi-techniques information in multiphasic degradation models. And so the interaction I've seen is with WG2. So as you have seen in my team, we have some papers about the performance and limits of embedded sensors, fiber optic sensors, the assessing of the spatial variability from SHM, the damage detection from image processing, and the underpixel measurement through virtual image correlation and underwater inspection. And so when we look to a study case, we have some of them because we made some instrumentation and some monitoring of structures. And I had a question I already asked to Sebastian. Quite a lot of people here are working on jackets, offshore structure, on wind turbines, and so on. And I was thinking about if we could have one common design for the cost action in view to compare and to make either the benchmarking and to put our sensors in this virtual or real structure. So that's the fact sheets I want to propose. If you want more information about the quantification of uncertainty here, I have a chapter in a book where I have some example, and we can put that in a WG2 too. And actually, we have a conference in France, that's the European Reliability Safety and Data Acquisition Conference in Clermont-Ferrand. So I think that it's still open. And I would like to analyze the region des Pays de la Loire to supporting two projects and the EARSET in Ireland for supporting some of them. Thank you.